Okay, and we're back. Sorry for anybody that's watching this over again or further. Anybody else? So here are the answers A through D. Sorry, I started a little late. Let's get to E now. I want to switch colors. Interval where f is increasing. Now remember that if it's going up the hill, then it's increasing. So I say all the way up until this point, right? All the way from there to there. So from -2 to +1. From -2 to +1. So -2 to +1. And I would say we would use parentheses because at 1, is it still increasing? No, at 1 it's reached its apex. And we'll talk about what that means in terms of the derivative.
I think on the key it's shown as brackets for both.
Is it? Okay. I'll be a little bit lenient on that. F there. State the domain and range of f. Okay, the domain, now this should be brackets. There's no open circles there. The domain looks like it's going from -2 to +1, 2, 3, 4. The domain is brackets. -2 to +4. And the range is going from -1 all the way up to +2, 3. Now it says sketch the negative f of x on the same graph. Sketch the now what is that? Reflection over the what? X-axis. Right? Reflection over the x-axis. Now honestly, what we could do is just kind of like sketch it using some key points there if we wanted to. Like for example, we know these points are there, right? So it was 1, 3. So that means it's 1, -3. 1, -3. Oops, a little bit down there. This is -2, -1. So this is -2, +1. This is, what do we have? -0.6, 0, which stays the same, right? And here, if I'm going to reflect this over the x-axis here, that should just shift downward there. Okay. So it should gradually slope up to an apex and then level off there. Use the shape of the graph on the other side. All done? Yeah. All right. Questions on number 1? Okay, let's get to number 2. State the domain of f of x, identify any holes or asymptotes. State the domain, and then identify any holes or asymptotes. Now, what do we have to think about in terms of the domain of a rational function? Well, the denominator can never be 0, right? That's really what I'm asking you. If I'm looking at a rational function, the domain cannot, it's all numbers but when the denominator is equal to 0. So let's see when that happens. X to the 4th minus 13x squared plus 36. All right, now this one's kind of a weird one, but I can factor that down. That would be like saying, okay, factors of 36 that add to get to -13. That's, what does that come out to be?
4 and 9.
4 and 9. Thank you. I was like 15 and 2. Like I was thinking about 30. 4 and 9. -4 times -9. So x squared minus 4, x squared minus 9. Now, can that reduce as well? Yeah. So that is x minus 2, x plus 2, x minus 3, x plus 3. So what is the domain? Now, I would accept if you wrote the domain in a couple of different ways. You could write it in interval notation, but it honestly might be better to write it like this. The domain is when x is not equal to plus or minus 2 or plus or minus 3. All real numbers except for plus or minus 2 or plus or minus 3. Now, that's the domain. Let's identify the holes. Now remember, this is the denominator. So this is x minus 2, x plus 2, x minus 3, x plus 3. Well, look at the numerator. I would factor out an x, and I get an x squared minus 4. And isn't an x squared minus 4, isn't all of that x minus 2, x plus 2? Remember that holes arise whenever things cancel out. So the holes here are at x equals plus or minus 2. If we wanted to, we could plug it in to see where the holes may come up. But I'm okay with saying the x values. So this reduces all the way into x over x minus 3, x plus 3. Now we have to check any asymptotes. Okay, horizontal and vertical asymptotes. Remember that there are horizontal asymptotes. Actually, let's go vertical asymptotes first. Those are the easy ones. Vertical asymptotes. Where are the vertical asymptotes? Where the denominator equals 0. So we can say x equals plus or minus 3. Now, for horizontal asymptote, we have to check, okay, bottom heavy, top heavy thing, right? On the bottom, if I FOIL that back together, I get x squared, right? So it'd be an x over an x squared. Hey, there's Carter. Welcome back, Carter. We're only on problem 2. So we've got an x over an x squared. So this is bottom, excuse me. This is bottom heavy. Remember, that means that there is, if it's top heavy, there is no horizontal asymptote. If it's bottom heavy, the horizontal asymptote is at x equals 0. If it's equal, then you take a look at the leading coefficients. I'm sorry, y equals 0. So we say that this one is y equals 0. Again, that's because it's bottom heavy. Remember, if it's top heavy, there is no horizontal asymptote. If it's bottom heavy, it's at 0. If it's equal, then you have to take a look at the leading coefficients. And I believe that's all we got there, right? Plus or minus 2. We've got the domain, the holes, the vertical asymptote, and the horizontal asymptote. In my opinion, that was one of the hardest questions out of the Chapter 1 test. That was the most commonly missed question out of the Chapter 1 test. Because a lot of people forgot how to find holes. A lot of people forgot how to find the domain and range. And it just kind of got a little muddled beyond that. Okay, let's take a look here. Given the piecewise function, sketch the graph and find those 3 coordinates. Okay, now for a piecewise function, let me get, let me first calculate these 3 points. Let's find f of negative 3. Okay, if I want f of negative 3, that's below 1, right? So that means it goes in the bottom. So we would say 2 times negative 3 plus 1. So negative 6 plus 1 is negative 5. So negative 3 comma negative 5. If I want to find f of 1, well, that's still in the bottom because that's or equal to 1. So I would say 2 times 1 plus 1. So that's 3, 4. Oh, sorry, 2 times 2. Well, I can't do math. 2 times 1 is 2, plus 1 is 3. Yikes. And then we find f of 4. Okay, greater than 1. So I go in here. 4 squared minus 2. So 16 minus 2 is 14. All right, now let's get a graph real quick. I'm going to go in here. My content. Let's go with 6 by 6. See if that'll do it. Okay. Well, remember that in a piecewise function, the breaking point is where it's or equal to, right? Where it breaks for my domain. So, like, if you want to draw in a dotted line right there. Now, beyond that, to the left side, less than or equal to 1, it looks like 2x plus 1. So on the left side of 1, it looks like this. Y-intercept of 1 and a slope of 2. Rise 2, run 1. And I could put a closed dot right there. and then I could go down to left 1. So there is the line to the left, which makes sense because if I calculate -3, it's -3 comma -5. Now on the right side, it's x squared minus 2. Well, think about where that would come out to be here at 1. Well, what's 1 minus 2? -1. So I know there's an open circle at 1 comma -1. Now, what would it be at 2? 2 squared is 4. Minus 2 is 2. So 2 comma 2. What would it be at 3? Well, 3 squared is 9. Minus 2 is 7. So somewhere right up here. So it's a quadratic, so it's going to curve right there. Let me erase away the dotted line. And there we have it. There's my piecewise function. Again, you should always see the breaking point at where the domain shifts. Question about that one? No? Okay, let's take a look at 4. Find f of g and g of f and state their domains. All right, let's find f of g. F of g. Now remember, f of g, this notation really is the same thing as saying f of g of x. Right? That open circle is composition where the second function is inside the first. All right, so that means I'm basically going to find f of x squared plus 2. Right? So the x squared plus 2 is going in as my input into that 3 minus 4x, square root of that. So let's plug that in. So this gives me the square root of 3 minus 4 quantity x squared plus 2. Let's reduce that down a little bit. So that's square root of 3 minus 4x squared minus 8. So all in total, -5 minus 4x squared. I'm gonna pause on the domain part until we get done with the second piece, the g of f. Okay, let's find g of f. Okay, so that's g of f of x, which f of x is the square root of 3 minus 4x. Okay, now let's take that and put it into g. Okay, so that is square root of 3 minus 4x squared plus 2, which is nice because as soon as I square it, the hat comes off. So we have 3 minus 4x plus 2, so 5 minus 4x. Now, let's think about their domains. Remember, whenever you're working with composition, you have to check two things. You look at the domain of the innermost function, the inside function of the composition, and then you have to shift it if you need to based on your final. Like, for example, here. Take a look at my first one here. What is the domain there? What is the domain of x squared plus 2? All real numbers, right? There's no restriction on the domain on any quadratic. Okay, do I have to shift it? Do I have to change it at all at the original or in the final? Yeah, I do. -5 minus 4x squared has to be positive. It can be 0. It has to be greater than or equal to 0, right? It has to be positive. So let's solve that. We add the 5x, so -4x squared greater than or equal to 5. And then we divide x squared -5/4. And when I go to square root that, okay, plus or minus, square root of 5 over 2i. Yikes, that's weird. Because since it's a negative, a square root of negative, I got to have an I there. And then I can square root numerator and denominator separately. Square root of 5 over 2. So that's the domain. Okay. Now, let's think about the domain of g of f. What's my innermost function now? This 3 minus 4x. So I've got to look there. Sorry, the square root of 3 minus 4x. Do I have to restrict the domain there? Yes, I do. Because again, since it's a square root, 3 minus 4x has to be greater than or equal to 0, right? Subtract the 3. Divide by 4. Negative 4, excuse me. Flip the symbol. 3/4. X is less than or equal to 3/4. So I have to stay underneath 3/4. Now, I then take a look at my final and say, okay, do I have to restrict the domain anymore based on that? Well, what's the domain of this? All real numbers. So I don't have to restrict it anymore. This is the domain. I can't unrestrict it. I can't go back on it. Since I was already less than or equal to 3/4, I can't go backward. I still have to stay underneath 3/4. The only thing I could possibly do is restrict it more. Say maybe it turned out to be rational and I have some things where I can't equal 0 or whatever. That's the only time where you'd have to do something to it. Yes, Mr. Fobia.
For the first domain, why didn't we flip this sign when we divided by -4?
Oh, you're right. Thank you. That should be a less than or equal to, shouldn't it? Thank you. I did it in the second one, not the first one. Right? That was weird. My algebra students would be laughing at me. Questions on that one? Let's keep it moving. Ooh, got 5, 6, and 7 there. Using the chart, evaluate the following compositions. Oh yeah, this is fun. This is the one where I find g of 1 and then plug that into g, right? So what is g of 1? So if I want g of 1, okay, well that is, I got to evaluate g of 1. What is g of 1? 6. If the x value is 1, g is 6. And what is g of 6? 3. So g of 1 is 3. Okay, well, let's find g of f of 3. Okay, well, what is f of 3? 4. So I want to find g of 4. Well, what is g of 4? 1. Same thing. F of 1. Okay, find f of 1. Well, f of 1 is 3. So f of 3 is 4. Questions about that? So using those charts, the input, just match the input with the output. Keep plugging it in if you need to. All right, let's take a look at number 6. E to the 2x minus 1 is equal to 3. Still in chapter 1 step. This is all still reviewed. All right, to solve an e to the x, I need to take the natural log, right? Just spiral it. Log base e of 3 is equal to 2x minus 1. So ln of 3 is equal to 2x minus 1. I add the 1 over to the other side. So ln of 3 minus 1. And then I divide by 2. So ln of 3 minus 1 over 2 is x. Let's see what the decimal value of that is. Just making sure you're paying attention. ln of 3, sorry, I was distracted by the helicopter. ln of 3 plus 1 divided by 2. 1.05. My neighbor's a helicopter pilot.
For ones like that, do you want it in decimal or can we leave it in?
Either one is fine.
Okay.
Either one is fine. I was up on my roof. He's actually a life flight pilot. Like he takes people to hospitals and stuff. And I was up on my roof doing my Christmas lights the other day, and he's like, the number one reason we get calls in the wintertime is because people putting up their lights, falling off the roof, needing the life flight. I'm like, thank you. Hope you don't jinx me. All right, number 7 there. ln of x squared plus 2 equals 7. He actually said, hey, Griswold, what are you doing up there? Relax. All right, ln of x squared plus 2 is equal to 7. Okay. So this is a log base e, right? I could rewrite it like this if I really wanted to. Log base e of x squared plus 2 is 7. E to the 7th is this, right? E to the 7th is x squared plus 2. All right, e to the 7th minus 2 is equal to x squared. So plus or minus the square root of e to the 7th minus 2. Let's see what that comes out to be. E to the 7th minus 2 square root 33.1 plus or minus 33.1. Questions on that one? Oh, there's 6 and 7. There's 8. Let's do 8. We got ln of x minus 2 plus ln of 3x plus 2 is equal to 3. All right, so addition of the logs means multiplication inside the log, right? So this is ln of x minus 2 quantity 3x plus 2 is equal to 3. FOIL in the middle there. ln of 3x squared. And then we've got a 2x and a negative 6x, so minus 4x minus 4. We got x squared, or 3x squared. We got our outers would be 2x, our inners would be minus 6x, so minus 4x. Oh, I think I got to do quadratic formula here. Gross. So remember, going from logarithmic into exponential, this would be like saying e to the 3rd is 3x squared minus 4x minus 4. So if I truly need to solve this for x, e 0 is equal to 3x squared minus 4x, and then I've got negative 4 minus e to the 3rd. Negative 24.1 minus 24.1. And then it looks like I got to do some quadratic right here, quadratic formula. The opposite of b plus or minus the square root of b squared minus 4ac all over 2a. Pop goes the weasel. I took the negative 4 and I subtracted the e to the 3rd over the other side.
Gotcha.
Yeah, I did this. Negative 4 minus e to the 3rd. All right, so let's get going in our discriminant there. 16 minus 4 times 3 times this negative 24.1 rounded. 305, let's square root that. We get something, let's say 17.5. 4 plus or minus, not square root anymore, just 17, of course, 0.5, all over 6. And now let's run those numbers. 4 plus 17.5 over 6 is 3.6. And then 4 minus divided by 6. Negative 2.25. Those are my x values to make that true. Now, I should go back in and see, ooh, this is fun. Can x be negative 2.25? What if I plug that back in? I would have to say negative, or natural log of negative 2.25 minus 2. Non-real answer. That's the next iteration of calculators are going to have sound effects with them. So like when you get a non-real answer, it's going to be like wah wah. Or like maybe when you hit your enter like on a really long equation, it's going to be like da 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 da.
You could be rich.
Hey, you know.
Do it.
TI, if you're out there, Texas Instruments, I'm waiting for the call. I'm just a wealth of ideas. Wealth of ideas. Let's keep it going. Hey, let's do a linear regression.
Oh. No, I can't.
Oh, this is easy. The table shows average U.S. retail residential prices of electricity from 2000 to 2012, measured in cents per kilowatt hour. Find the linear model of the regression line. Now, you stats folk, can you do this in your calculator? That's so nice. That's so nice. That's so nice. My stats class, I was not able to use a calculator. We did this by hand. Had to walk to class, uphill, both ways in the snow. Okay. Okay, remember, to get to a linear regression, stat, edit. I need to clear out my lists. Remember, clear down. And then we got years since 2000. 0, 2, 4, 6, 8, 10, 12. Okay, 0, 2, 4, 6, 8, 10, 12. Whoa, that's not 12. On the right side list, we got 8.24, 8.44, 895, 10.4, 11.26, 11.54, and 11.58. Just double check you didn't. Look at that. I did that. Number 12. 11.58. Always go back and double check your data. Make sure you didn't screw something up. Grace over there Snapchatting. All right, now let's use a linear model. Stat calc 4. There it is. There's my linear model. Y is equal to 0.33x plus 8.07. There's my linear model. Is a linear model appropriate? Yeah, look at my R. Look at my R value. When did that go up?
Oh, just 3 seconds ago.
My linear model is good because my R value is relatively good, right? Anything above 0.9, I would say is good.
What's the difference between the R value and the R squared value? Like, do you even use the R squared?
Well, can my statistics folk, do you guys get into that? The difference between R squared and R?
Dude, I don't know what we did last week. It's just like,
Kylie, do you know? Did you guys talk about that at least?
I think he said ignore it.
Well,
that
honestly,
sounds right.
the difference between R and R squared is like, literally, R squared is just that value squared, right? So it's taking the amount of error and amplifying it. So if your R squared is good, that means that the strength of your correlation is even stronger than just an R value. That kind of, because R stands for residual. So basically, like it's taking all those points that are away from the line and calculating the difference away.
Yeah.
Right? And then it's squaring all of those. So it's only amplifying the residual, which means that if you've got a good R squared value, it's even better.
Well, wouldn't if like you're always gonna have a decimal for R, wouldn't R squared always be like a smaller value?
Yeah. Because R squared, and so that means the closer you get toward 1, that's even like less of a probability of happening.
Okay.
You know, because you're squaring those residuals and making them even bigger, which making your R value even smaller.
Okay. All right.
Does that make sense?
Yeah.
Kind of, maybe.
Who teaches stat?
Mr. Marco.
Mr. Marco.
I don't know if I'm taking that or not. That might be.
Find the linear model. Done. Is the linear model appropriate? Talked about it. Use your model to estimate the average retail price of electricity in 2005 and 2013. So honestly, now let's do it in our calculators. I'm going to go into y equals. I'm going to turn off my plot too. I don't know what that was. But I'm going to go into my y equals and go vars. Remember, it's in vars, statistics, EQ. And there's my regression equation. Vars, stat, EQ. And now I'm going to zoom stat this. Zoom 9. Whoa, box and whisker plot. What are you doing there? What?
Fox and Whisker Plot.
That's what the fox is that whisker.
Grace didn't take stats. She wouldn't know.
Okay. Yeah, I had plot 1 on a box and whisker. Okay. We do that in Algebra 1, I'm just saying.
Grow up.
Zoom 6. Zoom stat now. Okay. There we go. Now, based on the graph, would you say that a linear model is appropriate? I don't know. I mean, like, it looks like it could be something better. Like maybe that had something with this shape. You know what I mean?
Yeah.
But for our purposes here, the R value told us that it was going to be all right. So I just say okay. Now, let's go in and run these numbers. 2005. Well, remember, second calculate the value of 5 because it's years since 2000. So at 9.27 or 9.72, excuse me. And then stat calc, or not stat calc, just come on. Second calc, 2013. Not 3. Calculate value of 13. Okay, 12.37. So those are my two values. And then it says, in what year would the price reach 15 cents per kilowatt hour? All right, so now I need to go into my y equals and say, okay, I want to know when the y value, the threshold is going to be 15. I'm going to zoom fit this. So I'll see 15 coming across. I don't see the intersection point here, so I got to zoom out a little bit. Zoom 3, enter. There it is. Second, calculate the intersection point, 20.9. So in year 2021, in 2020.9 or whatever that would be, 0.9 of a year in, December of 2021 or something like that. Okay. Yeah, sure. From what point? Finding the y value? Going through that part? Okay, yeah.
No, just the last one.
Just the last one, just the plugging in. Got it. So if I know that the y value needs to be 15, I go plug that in right there, right? So we were here. We plugged in 15, and then I was initially here. So let me go back to that. Like this was our window, right? To get the 15 to show up, the best way to do that is to fit. Zoom fit. Because that's going to show us our regression line and then 15 coming across the top. Now, I need to see that intersection point, which is somewhere around out here. So I'll zoom out. Zoom 3, and then you just have to hit enter to make it happen. And then now here, second calculate, intersect, 5, enter, enter, enter. There it is. Make sense? Let's do 10 real quick. Is the function continuous at 3? That's what we're looking at here. What should I see if the function is continuous at 3? I should see these where this happens, and this happens should equal, right? Because there should be no gaps or breaks. All right, so let's see. Square root of 2x plus 10 is going to be square root of 2 times 3 plus 10. Let's see where that ends up. So 16, 4. If 4x minus 5, when I plug in 3, doesn't come out to be 4, it is discontinuous. So that's 12 minus, I don't know what I put a parenthesis there. So that's 12 minus 5. Is this continuous at 3? No. Not continuous. And the reason being is because the limit as x approaches 3 from the left is 4, and the limit as x approaches 3 from the right is 7. So the limit from the left and the right don't match, so therefore there's a discontinuity there. Find the value of b such that it's continuous at 6. All right, so remember that this should be true. 4 times 6 minus 5 should equal 6 squared minus b. Right? That should be true if this function is continuous at 6. So 4 times 6, get out of here. 4 times 6 minus 5 is 19. 36 minus b. We subtract 19 minus 36, and we get 17, negative 17. So 17 is equal to positive b. There it is. That's my b value. 17 would make this continuous at 6. Okay. Yes, sir.
Do we need to know the names of like the discontinuities or no?
I would. Yeah, I think. Do I ask that in a little bit? I guess I don't. Oh, 21. State where it would be differentiable. Because remember, that's if it's continuous, then it's differentiable. So, like, tell where it's not differentiable in y.
Yeah.
You would say, like, okay, it's not differentiable at -1 because there's a jump discontinuity.
Mm-hmm.
Or I'm sorry, removable.
And then like choose like the corner.
Yeah. Yeah. So yeah, that implies that you want to know the names of this discontinuity. Well, I only got through 10 questions. Jeez. I'll get a jump on it tomorrow. We'll get to question 30 by tomorrow, shall we? Let's do 20 questions tomorrow. 20. Let's go.